Welcome, and Emma, and the floor is yours.
Thank you very much. Thank you for the nice welcome. So this is work that I've been doing jointly with my colleague Duncan Lee, who Kathy knows, and Ailey Jack, who was our PhD student and is now our colleague. So she's moved up in the world, but not quite an adult yet. Yeah. So it's, as it says, spatio-temporal modeling of respiratory risk with changing boundaries. So that was the spatial-temporal modeling of respiratory risk was the original idea, and then we discovered the data didn't quite match to what we hoped it would, and so this is how this particular method came about. So why do we care about disease risk? Well, if disease risk were constant for everywhere, it wouldn't matter so much. We wouldn't actually have to make any changes. Knowing where disease risk changes in space gives us an idea where we should basically invest and try and intervene. So having an accurate or semi-accurate estimation of how the disease risk looks over space is fairly important. Disease risk changes partly because of behavior, so you have issues with alcoholism, you have risk-taking behaviors and so on, depending on which disease you're talking about. Deprivation is one of the biggest drivers, obviously, of disease. Also demographics, if you have areas of the space that have a lot more elderly people than young people, then you will tend to see higher risks of disease there because just simply of their presence. So we care about how it changes over space, and we also care about how that reflects the inequalities that underlie that. So if there is a particular difference based on social groups or population areas, again, this means that we can actually look to improve things, hopefully, and make interventions. So you can talk about health inequalities within countries, between countries, in subsets of countries, and so on. So you can define it wherever you want to, in terms of, as long as you have spatial data. The UK is not a good example in Europe, well, if we can even be considered to be in Europe anymore. We have a lot of inequality, so there's a huge difference between certain areas in terms of risks of diseases. And for mortality risk as well. And a lot of it's driven again by these inequalities, this deprivation. Scotland is even worse. So Scotland is known as the sick man of Europe because we were pretty much near the centre at the beginning of the century in terms of life expectancy, but everyone else started overtaking us. So we're now right at the bottom of the pile. So that's a problem, just as an average health risk and life expectancy. Even worse is the width, the sort of variation around that, how much it changes. It really matters where you live, what your life expectancy is going to be. And that's been shown by Popham and Boyle in 2011. There have been updated studies since then. If we looked at 2015, you get almost a quarter century of years more health in the most affluent area versus most deprived area in Scotland. That's unbelievable. I think that's shocking, yeah, essentially, yeah. So you have people who may not even make it to retirement, basically. It's very good for pension funds because they don't have to pay out, not so good for the people. So there was a reduction in terms of inequality. So while the general average life expectancy was not doing great, it was improving, but not improving as fast as other countries, at least the variation around that between the 1920s and 70s narrowed a little bit. So obviously things have changed since then, given 2015 we can say this. So there's actually been a widening of inequalities again. So Glasgow effect, Kathy will recognize this. It's another word for why is Glasgow so much worse than what you would expect when you account for all the factors compared to anywhere else in Scotland, compared to the UK. I still love Glasgow. I recommend you coming to visit. Please don't cancel your visit. But there is a huge shift in a range of health expectancy and life expectancy across. So this is our dinky little subway. We have one little line that goes counterclockwise and clockwise, and it takes under half an hour to do the total loop. And Hillhead here has a life expectancy for males of 80 years, 2 years ago. Govan, which is literally 8 minutes down the road, has an expectancy of 66. That's tiny, that's within 10 kilometers. That's huge. So there's these dramatic changes, not just that we're smoothly varying, there's big shifts in areas that live next to each other as well. So repercussions of this are obvious. I mean, if we actually managed to improve all of the really deprived areas to be on the level of the least deprived area, there'd be 20 billion in savings in terms of the budget. This obviously puts a huge burden on the NHS, and given that the Conservative Party for the last 10 years has been gutting its funding, and this is partly where the problem is coming. The Scottish Government has actually made this a priority, so in 2007 and 2017, there were task forces set up to deal with the health inequalities, and in 2011-12, it allocated 170 million to the different health boards, and these are particular boards that deal with regions across Scotland. And so each health board got a certain allocation of that 170 million. 170 million sounds like a lot until you think about the fact, that there's 4 million people and how much does each disease cost, so it actually needs to be very targeted with how you use this. So when I say Scottish health boards, this is a map of lovely Scotland. Do visit, it's beautiful. I'm living in Glasgow here, this little green area, and so this is part of what we call a central belt. Glasgow and Edinburgh sort of make up this line that bisects Scotland and tends to have most of the population of Scotland is the sort of industrialised area, the urban area. So I'm going to focus on the Greater Glasgow and Clyde Health Board for the data we're going to look at today. So it'd be nice if we had information about individual diseases and cases. Obviously that's not possible because of patient protection, so we have to deal with aggregation. And in this case we're looking at aggregation across small areas. So the areas that we're going to be looking at are smaller units that are called intermediate geographies. You'll also see them referred to as intermediate zones. People seem to change randomly between those names. They're essentially the same thing. So within Greater Glasgow, that's split up into 272 of these intermediate geographies. Greater Glasgow covers about a population of 1.2 million. So out of Scotland's 4.5 million, that's quite a large proportion. It's the biggest city. So the intermediate geographies were designed to try and have roughly 4,000 on average residents. So obviously as you were in urban areas, those geographies, the area that needs to capture that is quite small. If you move out to rural areas, obviously that becomes much larger. So there is a variation in size in terms of these regions. We have yearly data from 2006 to 2016, and we have information about respiratory disease, so we're trying to look at risk for that. So we thought this was going to be very straightforward. We have 10 years of data, we'll do a time series analysis, spatial analysis, and call it a day. Oh, this doesn't show up well. I'm sorry. There are black lines and dashed white lines that indicate where the regions are defined, and they don't always match up. So you can see here, there's a black region here that has been split into two by the white lines. So between 2001 and 2011, they redefined the regions. Now, not every region changed, but they introduced new ones. You can see this little white region here that didn't exist before 2011. So our data is recorded on different partitions of the space. So at that point, we're in trouble because 2011 is almost the midpoint of our time series. So we could analyze before 2011 and after 2011 separately, but that's not really going to tell us very much about improvement or disimprovement over time. So we sort of groaned and shook our heads and decided we had to change the methodology. So we can't actually apply them to the original areas because they change over time. We can't do this because we have to be able to compare these areas in terms of our inference, and so the misalignment means that we can't do that. Our approach is going to be to try and actually project the areal data into a grid below that doesn't change over time. So then we can analyze the changing patterns across the grid without having to worry about that incompatibility, that misalignment. And that sounded really straightforward, which is why we have like 4 pages of equations following this. In order to do that, we think about how we actually would randomly assign, based on certain probabilities, the counts of disease in the areas to the grids. And we do that multiple times because one draw really doesn't really capture what the variability in that does. But once we have these imputations, we can just analyze them across time and look at what the inference says. So we split our area of Greater Glasgow and Clyde Health Board into these intermediate geographies. So these A's are going to be our areas, our sub-areas, intermediate geographies, and they're indexed by KT. Because if you remember, the intermediate geographies change depending on which year you're in. So before 2011, you have 254. After 2011 to 2016, you have 257. And additionally, the naming of them has also changed because some of them have split and some of them have merged and so on. We have the disease counts, these aggregated counts, which is the number of admissions to hospitals in Scotland with a main diagnosis of respiratory disease. Remember, this is before COVID, so we don't have that sort of spike in each of these particular areas at each particular year. We can also calculate the expected counts. So we want the expected counts because we want to remove the effect of gender and age. So if some areas have more elderly population, we want to account for that and not just say that this area has very high risk. We know that it's because the population is different there. So we want to have an expected count and compare the observed to what we would expect given that demographic. So we have those expected counts. We got those from the NHS. We had to pay through the nose for them, but we got them. So how we started out was with this grid. We took our region of Glasgow, we put this grid on top of it. Each of these grid cells is reasonably small. It's a half a kilometre times a half a kilometre, so a quarter kilometre squared. So on a fairly high spatial resolution. There are 4,807 of them, and obviously they don't change when you go from 2001 to 2011. But you can see again that difference. If you look at the top left corner here, you have a big region that's obviously been split, and some part of the region has been merged in a different way when you go from 2001 to 2011. So there are not insignificant changes to these areas. That's why we have to do this. So what we have, this is the simplified version so we can actually see. So the red areas drawn very badly are our areal units, which are obviously non-regular. We know the data for the counts and expected counts in there. What we want to do is find out what the values in the grids are. And so what we'd like to think is, okay, if I'm looking at grid 5, a proportion of the counts from area 1 should come in there, and from area 2 and area 3. So that should combine in some way, but we want to think about how we actually combine those. So that's the general idea. So we're going to think about the area of these things. So if I have a very small proportional intersection, so the proportion of intersection of A1 with G5 is about a fifth of what this particular area looks like. For A2, it's even smaller. It's a very tiny sliver. So we need to know what the area of these intersections are relative to the area of the grids. So we're going to define little a as the area of the grids, and we can talk about the area of the intersection between a particular grid cell and a particular area unit or intermediate geography. We also, thanks to Reese et al., have the population estimate for 2015 of each of the grid cell counts. So that gives us information that we can use to divide up these things. So we can think about, if we think it's roughly proportional to population, how these things should be divided. And so we can think of the P of G of I given AT. AT is just our particular study region at time T, which is just going to be Greater Glasgow. So, first things first, get rid of the nonsense ones. If we have zero population in a grid cell, we don't really care about estimating risk because it doesn't make sense. So any grid cell that has zero population right the way through is going to be removed. Given that we might have some regions, some grid squares that are not completely within the region, so here grid square 9 is outside the region defined by A1 to A4, so we might not necessarily want to assign all the population from G9 to that. So how we're going to do that is basically just, if all the area outside is unpopulated, then that's just going to be, or population is just going to be equal to the same thing. The population of the grid square given the areals that we're studying, if there's another health board that we're looking at, is proportional. So we take the population in the grid square and we look at the proportion of the intersection over the area of the intersection over the area of the grid square. So we count basically how much of this is actually included within the grid square. So proportionally to that, our population here might be roughly 2/3 because only 2/3 of it is within that range. Okay, so that's a subset of the original grid that we're going to be looking at. We have now the population on this grid, and we're ready to go. So this is what the subset of grid looks like. So unsurprisingly, when you see these really big areas, they're rural areas, so there's not a lot of population, so that's where you see all the cells being removed. You also see grids that are removed when they're intersecting with the sea and the river, so obviously no one actually living there. So, coming back to what we have expected counts and observed counts. All of those are on our original areal units. We want to project them down to this grid. But we want to make sure that we preserve the total number of expected counts, right? Because essentially we're dealing with the same population. So when I go from all the expected counts in those pale areas to the grid, I want to make sure that I don't lose anything. So I want to make sure that the sum over all the intermediate geographies of the expected counts of those areas is equal to the sum of the expected counts that I calculate for these grid squares. So I want to take a look at what the expected count is for the intersections of the areas and the grid squares. And so given that I know that obviously the expected count for a grid square is going to be the sum of all the intersections with all the areas of that grid square expected counts, then I can basically just set this equal to that. So it's giving the roughly relative to population size, it's allocating these expected counts based on that. So we have for the expected count for this intersection, it's going to be equal to the expected count times the proportion of population that we find within that intersection. And then we can estimate the population by, again, allocating these according to the areas. All right, so if we do take a look at the original data, and so remember here, so this should, 2006 up to 2012, we're still using the 2001 intermediate geographies. So that's why the box plots are colored differently, so we can't directly compare the box plots here in white to the ones in green. But we can get an idea of what's going on. So if we look at one here is the standardized incidence ratio, where if our expected count equals our observed count, so we don't have elevated risk. Below 1, we have less risk. So everything here compared to 2006 is above 1. So that's a bad sign. So incidence of respiratory diseases are definitely increasing. Now there's some for which the risk is below, but as we get further and further towards 2016, those are above 1. So that's bad. And we also have some extreme outliers here who have extremely high risks. The other thing that we care about, so this was the average, is width of those box plots, right? That gives us an idea of how unequal things are, how widely spread these risks might be. And so in 2006, we had the medians, sorry, I'm skipping ahead. So in 2006, we had an average median of 1.05. It goes up to 1.374, so that's a huge increase in risk. And the box plots are increasing in width as well. Oh gosh, you can't see this at all. All right, yes. Darker areas, bad. So the middle of Glasgow here is looking bad. It's getting darker over time, but you can see the sort of pattern is changing as well. So not only is the color getting darker over time, it's also changing where the worst parts are located. So it's not just a case of everything moving in the same way, there's also changing spatial patterns as well. Okay, final step, a last bit of equations. We have the expected counts now on the grid squares. We need to impute what we think the observed counts should be divided up to among those grid squares as well. So we have our observed counts of respiratory disease admissions in each year T for each area AKT. But what we want is the year T for grid square I. So we can again see that we should be able to look at these as basically the intersection across all of the areas with that grid square. So if we have, if I'm interested in YT, I know that YT will be coming from A1, A2, and A3 again. So this is just going to be equal to the sum of those counts for the areas that the intermediate geography intersect with the grids. So what we do is we basically take a look at partitioning the values of YTAK across those intersections, right? So I want to randomly generate counts for all of these intersections given what I know YTAK to be and where I know that there are intersections between that. So some of these will be 0 because, for example, apologies, if I'm looking at area 9, grid square 9, I know that A1 isn't intersecting there, so we're not going to allocate anything from A1 to grid square 9. But we need to find some way of generating these proportions, these probabilities, to sensibly allocate some of these counts across the different grid squares for each of the areas. So again, we're using the idea that we want the probabilities to be proportional to the proportionate area. We're assuming, and this is an assumption we're making all the time, that these things are roughly uniformly distributed across areas. If they're small enough, that's a relatively okay assumption to make. For larger areas, we might be a little bit worried about that one. So basically I'm saying, okay, I want to be proportional to the area of that intersection. So the probability of assigning a count from area KT to grid I is proportional to the area of the intersection of those two divided by the total area of AKT.
What about the mountains? What about the mountains and lakes?
Mountains and lakes, we have removed those grid squares because if there's no one living there, we're not estimating these. So we've cheated and basically taken those out.
The limited area.
Yeah, exactly. Yeah. And so we also want the number of cases that we would expect. So we want to keep that proportional to the expected counts. So this is where we run into problems. So assuming that we have sort of a population density we want to include, because we know about the expected counts given the different demographics, we want to be able to say something about that. But we don't know the risk multiplying that expected count. And so what we do is we take our areal units and the center points and basically call those points and do a geospatial kriging. It's very simple, it's very unsophisticated in some ways. And then we predict for the center points of each grid. So not terribly fancy, but it was seemed like the easiest way of getting that estimate of that risk at time t of area KT. So we can use those predicted as then to predict the risks at time t for grid square I. Because these things are pretty skewed, disease counts generally tend to be, we do use the log and then we exponentiate up. We are modeling over time, but this is essentially calculating a probability for imputing data for each time point. So we don't want to estimate this across time, we don't want to smooth too much. So we do actually do the kriging each year separately. And basically we use an exponential covariance function and the GeoR package, the standard defaults. Okay, final one, and then we get to actual results. So I have my set of observed counts for this area for this time point. I want to divide them up in the intersections of that area with all of the grid squares, knowing that some of these will be zero. So my weights and probabilities for this multinomial are then going to be that expected counts under the kriging model times the proportionality of these areas. And then we just divide that by the sum across all grid counts because we know that this is supposed to sum to 1 to give a probability. We did actually initially just look at a single draw and ran the model on that, and then we started to worry that we weren't capturing the sampling variability, so we suddenly thought, okay, multiple imputation sounds like a good idea. But multiple imputation brings up another question, which is what do you do when you have multiple data sets? Do you take the multiple data sets and average them to try and get a sort of roughly single point estimate of this? Or do you run the model on each of the data sets and then average the results of the model in some way? So we're going to call that data averaging versus posterior risk averaging. So we tried both just to see what we had. So for the data averaging, basically if we have P of these draws, we just literally average them. So the number of counts for the intersection of area AKT with grid square I is just the average of the multiple draws across the P realizations. Downside of this is it doesn't preserve the counts. So the sum of all counts in the grids doesn't necessarily equal to the sum of all counts in the original data because of that averaging. So that's one downside. We did look at doing the mean and median. So mean seemed to give better results. It seemed to be closer to not losing too much of the counts when we were trying to keep that equality there. And then we also looked at posterior risk averaging. So we fitted spatio-temporal models within each set, and then after that we've just combined the samples from the posterior to try and get the estimates. So very straightforward approach. So The model that we fit actually wasn't that interesting after all that. All the work was in creating the data set and just imputing these values. So we have the observed and expected counts finally on not just the grid squares. We have then want a model for our observed counts given what the expected counts were and the risk of the disease that this wants to be. So we want to estimate that risk of disease. That's what we want to be able to map, to see where the risks are higher and risks are lower. So we just used a hierarchical Poisson model, where essentially Poisson mean is just equal to the expected counts times the risk, and the log of the risk is equal to just an overall intercept for the whole data. Then we also have a random effect for time point t and for grid I, plus random effect for the time point t. So the temporal trend is roughly captured by delta t, and the spatial trend or spatial pattern is going to be captured by that random effect phi t. Okay, so what we want to do, why we want to do that spatial effect is we think that there should be some smoothness in these things. So we would expect if we have a high risk in one area, then the neighboring areas should also have fairly high risks. And so that's why we're trying to do this. We think that the observed counts have noise in them, so we're trying to find that smooth underlying risk surface. So how we classify that is introducing what we call a neighborhood matrix. So the neighborhood matrix basically just says which points neighbor each other. So usually what happens is, go back to, so let's say I have area 1, area 2, and area 3. Well, area 2, area 3, and area 4 are all neighboring area 1, so those would be the neighbors, right? If I look at grid square, it's much easier, it's regular. So if I have grid square 5, then my neighbors are grid square 2, 4, 6, and 8. But we've removed some of the grid squares, right? So there will suddenly be missing neighbors. So what we wanted was to have roughly regular numbers of neighbors for each point. So we chose to do a nearest neighbors approach where we chose the nearest 4 points in terms of the grid squares. And we chose 4 neighbors as being a reasonable number. And if there was an asymmetry in that, so one was a neighbor of another, but the other was not that's neighbor. So area 1 was neighbor of area 2, but area 2 is not the neighbor of area 1. We made both of them neighbors. So if I get rid of, for example, grid 4, now at grid 5, I'm missing one of my neighbors. So I'll look for something that's closer. So I might choose grid 1 as one of the nearest neighbors. All right, so reminding you what our grid looks like. Our spatial effects part, how we're mapping that spatial pattern, is based on these W's that indicate whether or not we have neighbors. So Wij is equal to 1 if I is a neighbor of j. It's equal to 0 if they're not neighbors. So this just basically knocks out all the non-neighbors. So this 0, when they're non-neighbors, knocks those non-neighbors out of that sum. So the effect, the random effect for grid square I, given all of the grid squares, only really matters on the neighbors, only really relies on the neighbors. So it becomes basically a weighted average of the neighbors' random effects, and you can see that the variance will also decrease the more neighbors that you have. So that's why we tried to keep the number of neighbors more or less fixed. We kept this rho S, which is roughly a level of how correlated things are. So the higher rho is, the more correlated, the more similar we expect neighbors to be to each other. So we estimated a single one across all years for this. Tau squared, however, we allowed to vary because we thought the variation might be different. Delta t is essentially the same specification, but here it's much easier in terms of neighbors. So time point before you and the time point after you, your neighbors, basically. So you're averaging out those. We used MCMC, Gibbs Metropolis steps. Happily enough for this particular model, once we had actually done the work to get the grid square information, we could just throw it into the Carbase ST package. And I'm going to give a sort of advertisement here for Duncan Lee. He has 2 packages, Carbase and Carbase ST, which basically let you be a Bayesian without having to be a Bayesian. You can fit models without having too much information about MCMC. So if you remember, we looked at 2 different types of multiple imputation. One, we averaged all the imputations to give a single data set, and then we'd run that model on that. The other, for each data set that we impute, we're going to run the model, and then we're going to average the model's results. So we wanted to see which one tended to do better. And also if the model was actually fitting properly. So we did a simulation study. So in order to do that, we basically took the structure of Glasgow and we simulated data on the grid rather than on the areas. And then we aggregated up the grids to the areas and then threw away the grid information, basically pretended we didn't know it. And there are two different scenarios we looked at. We have an increasing trend of risk over time and no trend over time. So we pretended that we didn't have the grid square information, we did the multiple imputation, and we tried both aggregation methods. And so we wanted to compare them. You have to forgive me here for being very non-Bayesian. I realize bias and root mean squared error and 95% coverage are all kind of frequentist style estimates, but it's the easiest way of checking to see when you actually have generated only a single data set, how it goes. Okay, so when we do this, we essentially just look at what our true value for the risk was, which we generated, versus what our value for the J summation was going to be, and we summed that over 100 times. Similar thing for the root mean squared error, and then across the different samples we got these 95% credible intervals, and we saw how many of them actually covered the true value. So we have two scenarios. The top one looks at increasing trends, so comparing data averaging, which is the single data set coming out of the average with a model applied, to multiple data sets with multiple models, and then the averaging of the model output. You can see that the bias is slightly smaller for posterior risk averaging, so keeping all the multiple data sets and running multiple models actually makes a difference. The root mean squared error actually is better as well, and so is the coverage, so it's closer to the nominal 95%. For no trend, pretty much the same story, although not quite so dramatic difference in terms of bias and root mean squared error. Coverage, again, is not good for the data averaging. So this was just done on 20 imputations, so not a large number. It might possibly change if we had a larger number or a smaller number, it depends. So we have to investigate that further. Part of the issue, we think, for why the bias is worse in the data averaging is because we're not maintaining the counts. When we do the imputation, we maintain a count, but when we average the imputations, we don't necessarily maintain it when we're averaging. So to give you an idea of what's happening here, we have histograms of the different simulations. So we have bias being 0, data averaging, both of them seem to be roughly close to 0, but you can see that posterior risk averaging actually gets a couple really badly wrong. So in spite of the fact that the bias is better on average for posterior risk averaging, you could be really unlucky and actually end up in one of these outliers. No trend, similar idea. So both of them had outliers, but the more extreme outliers were in the posterior risk averaging. So on average, you should be doing posterior risk averaging, but it's a riskier process. You could end up in some of these unfortunate cases. RMSE, similar story, except you really can't see this. You'll have to take my word for it. There are some extremes in RMSE for data averaging and not for posterior risk averaging. And the same story holds for the no trend. So it's opposite in terms of RMSE. The RMSE is worse for data averaging and sometimes just if you happen to be unlucky. Coverage is more or less what you would expect. There's nothing really interesting on there. Okay, going back to the actual motivating data set, we have these intermediate geographies from our health board in Greater Glasgow and Clyde. We ran the model. We had 250,000 MCMC iterations, of which 150,000 were removed for burn-in, and then we thinned every 50 after that. We threw away quite a lot of the grid squares because we had a lot of rural areas included in that, so we only really have 46% of the grid squares that we actually have to estimate. So that's only 15,000. That doesn't sound so bad, right? 15,000, given that we only have 254 actual areas. So we're spreading out information awfully thin here, so that's one of the things to be aware of. In order to help a little bit with the model, we set the level of spatial covariance to be, spatial correlation to be 1, so very strong, because that was based on what our experience had been in the past. And we checked convergence with trace plots and Gwiki. Okay, you can sort of see this. This is 2006, the first year of the study. So dark areas tend to be around the south side and the west and the east side. If you move on to 2010, it's more or less a similar pattern. By 2013, you're starting to get much more extremes out in the far west side, which is not technically in Glasgow proper. It's an area called Clyde Bank. So this is Bearsden, which is actually quite a wealthy area, but there's also a not wealthy area right beside it. So this is why we would expect to see these extremes. 2016, it's getting darker. The outlook for Glasgow as well as the plot. And most of the stuff is staying the same place. Some of it has moved a little bit. So the pattern is changing a little bit. Mostly it's just getting darker in those same hotspots, which is in some sense good because we can actually focus on those areas. So take home from this is, the obvious thing from those plots is we really do have a variance in risk across the region. And it's not a huge region, but there are quite a lot of differences between them. Those risks don't stay constant over time, so you do actually need to do some sort of spatio-temporal modeling. Overall, we can see that the risk is rising. We can see darker and darker spots appearing, and it tends to be clustered around the same problem areas, those risky regions. So we tend to see those getting darker rather than new dark spots coming up. Which means we're getting worse and worse inequalities, right? The light spots stay light, the dark spots get darker, and so there's more difference between those areas. I realize that you couldn't see the plots terribly well. Take my word for it that the original plots on the areas are much less smooth than the corresponding ones because we've done some smoothing in our model. That may be good or bad. How much smoothing you do may remove some information, right? So if you have these really dramatic differences, you'll be smoothing out some of that. But assuming that for the most part the law of geography holds true, which is that areas close to each other tend to behave the same, it's probably not going to do too bad a job. So finally we have box plots that we can compare. So these are no longer on the areas, these are on the these are on the grids basically. And we have the risk set in 2011 at 1, so we're looking at how things change according to that. So in some sense, the change in risk doesn't seem quite as sharp, the median change, so that's good. However, if you look at the number of outliers, they're dramatically increasing as we increase the number. So there's these extremes, which is, again, implying that inequality is getting worse and worse. And that's sort of, even within the range of most of the data, we can see that's true. So the interquartile range for the first year, 2006, is 0.3569. By the time we get to 2016, it's 0.441. So even if we ignore the outliers, we still have this increase in inequality. So overall, we're increasing in risk on average over time. The variability is also increasing, and the number of outliers increasing. So the highest risks, including outliers, in 2006 was 2.2065. So that's almost over 100% increase in risk, right, compared to 1. It's worse in 2016. It's almost 3 times, right? So that's huge. On areas of risk, you usually expect to see 1.05 versus 1. So this is dramatic. The proportion of grids we actually estimate to have a low risk will be larger than the proportion of intermediate geographies with low risks, because essentially when you have an urban area, you aren't splitting that up into many grids, whereas you have a rural area, it's being split up in tons of grids. So there's more grid squares with low counts. And so that's part of why you're seeing a lower average here, but you're also seeing these extremes, because those areas that are almost entirely covered by a single grid will be really high for all counts. So the smallest intermediate geography is much less than 1 grid square cell, and you remember that's 1/4 kilometer squared. The largest one is going to be split into 400 cells, so there'll be 400 really low level cells. So you're much more likely to see these outliers. Okay, so this was a sort of summary of what I've talked about here with tons and tons of equations, but hopefully this is what you can take home from this. We looked at this multiple imputation approach mainly because we were worried about when we impute what the grid squares were, that we would be, in some sense, losing some of the information with the variability. And given that we're spreading on the order of 200 pieces of information across 15,000 grid squares, we probably do want to have some idea of how these things would vary. given that we were doing multiple imputation, we had two different aggregations, as you recall. So one was just data averaging, where we just averaged all of the imputations to one data set and applied our model there. The posterior risk averaging was where we applied the model to each data set and averaged the results. And so from the simple simulation study we looked at, it seems like posterior risk averaging in general, on average, outperforms data averaging, but you have to be wary that in terms of bias at least, posterior risk averaging has a risk of being more biased in extreme cases. Downside. Please do believe that Glasgow is a lovely place to live and a lovely place to be, particularly those of you who have been there and are coming in the future. But for those who live long term, there are issues with worsening disease risk. And I think as much as anything else, that's a reflection of the issues with budgeting with the NHS being cut. So there's much less early detection. A lot of things are not dealt with, so you have coughs and colds that become pneumonia that wouldn't have become pneumonia before, and so become hospital admissions. There's not so much social care, so if you're a young adult and healthy, you're fine in Glasgow. Apart from that, there seems to be a pretty bad story going on here, and that was even before COVID. So we at least can identify from this model areas that really do have problems, that either need interventions on the basis of the deprivation that might be driving these risks, or just in terms of early detection programs and things like that, to try and bring down those inequalities which have increased over time. Downsides of this. So we are kriging these standardized incidence ratios onto the grids. If that's not done well, then that's what the basis of this entire thing is about, and we're in trouble because those proportions in that multinomial that we're imputing from don't make sense. So part of the issue is that we have point values that we're taking from areas and how sensible that is. If we could get a little bit more information, probably we would have more values that we could trust about the kriging, but from where we're at the moment, that's where we're at. We want to go from multiple imputation to having an actual model for doing the grid square calculations within the Bayesian model, so that's the goal. So a single model rather than a two-stage approach where we're creating these imputations and then applying a model. Part of the issue with that is that we worry about these things getting over-smoothed, particularly if you're including smoothing assumptions twice. So that might be a downside for doing a single sort of holistic approach. Then, of course, you want to think about more than just one disease, right? These things are correlated, so you want to think about stroke, you want COPD, heart disease, those sorts of things. So you want to think about a multivariate approach, because you could estimate these things for each one separately, but there's definite connections, given that social deprivation is probably driving all of them. That's not entirely surprising. All right, so references, basically, that's it. Any questions? Stunned silence.
Yeah, I have a lot of questions.
Okay, right, I'm preparing myself. Yeah.
It's amazing. Yeah, so well presented that no statisticians can get it. I was wondering, because you make a lot of, or you're losing a lot of degrees of freedom by approximating the things.
Yes.
And, so I asked myself the question, because you at the very beginning you said it's somehow policy-oriented paper.
Mm-hmm.
I understand that academics make also methodological papers, and I like methodology.
Yes.
But still, finally, if you are going into policy implications, finally, still you need the regions, administrative regions, as they are.
Mm-hmm.
Yeah? So having the data on administrative level, then going to grid cells or whatever, and then going back.
Yeah, so trying
Yeah.
a double approach where you choose
So
the later ones as the reference and you're trying to move the earlier ones to that level.
My question is if there would be a huge mistake if you go much simpler.
Mm-hmm.
I mean, let's say using kernel density estimation, let's say in this bivariate version like a spatial relative risk.
Mm-hmm.
I mean, there's a population, there are a number of cases. Because I understood that you had the expected number of counts, depending on the privation,
Yes.
age structure, blah blah.
Mm-hmm.
Yeah, but still, if there is illness, we don't care if this is an old and ugly person or young and beautiful.
That's true.
Still, it is a case of illness, and money is to have the illness. Yeah.
But once you have the expected counts and you have the risk, you can multiply them together to give you the counts for each area.
So my question, because I know you can answer this because you asked me first. If you would do this very simple, I mean, taking the empirical data, maybe eliminating the mountains and lakes, just to avoid the areas which are not inhabited, and doing a kernel estimation each year as it goes.
Yes.
Without those approximation to grids, and having the conclusions on that level, would it differ that much?
In some sense, you'd be leaving out the smoothing over time, so that would be some degree of change. But yeah, if the kernel smoothing was capturing the spatial pattern appropriately, then yeah, that would work. And you could use it to predict on the areas that you wanted to predict on. The issue would be that you wouldn't be connecting it temporally.
Yeah, because the method is really amazing, but the question is what is the real value added?
Yes.
I mean, for policymakers, for science, definitely. But is the result so different? So
I can't speak because I haven't run it, but I suspect it wouldn't be too different. Yeah. I mean, part of it, both of the approaches, the kernel density would be trying to smooth things out as well. I'm not terribly familiar with kernel density. I have a very basic idea, but you can control the level of smoothing that goes on there as well, right? So would you be changing the level of smoothing that you do each year, or would you be keeping it constant across the years?
Your areas are not that huge, Kernel smoothing is like geographic weighted regression statistics.
Yes,
to be honest, it makes a circle around, and capturing the areas simply to run the smoothing function. The issues whether it should be adaptive or fixed, and what is the bandwidth as of
Right,
nothing more. So that's an issue, because there is a version for bivariate, because you know where the people are, but also you know where the cases are, where the cases are. So.
Yeah, I mean, I think that it wouldn't be too different, and essentially kernel density would give you the estimate of that pattern as well.
What is the value of taking this prior from Bayesian approach?
I mean, the prior in this case allows you to put that structure on that allows the neighbors to influence each other. So in this case, that allows you to. The prior information that you have is that neighbors should matter to each other, and so that's allowing that. I mean, for a lot of Bayesian, I think the prior is there to make it Bayesian, to make it work in Bayesian setting. Duncan will kill me for having said that, but I genuinely think that's true. I think that
those guys are not. I don't know whether you are the Bayesian or not.
I mean, I think priors and Bayesian statistics can be an incredibly powerful thing because they do allow you to incorporate information like that can be very difficult to incorporate otherwise. And I think that's why Bayesian statistics, particularly in spatial statistics, is taking over so much because of that. For things like regression and stuff, I don't see enough of a difference often that I think a Bayesian approach is that different from a frequentist. So what gain you get is not clear. But you can do all sorts of interesting things like expert elicitation of priors that really incorporate information that's otherwise very difficult to have. So, I was being a bit glib about Bayesian statistics before. I've slowly come from being a likelihood person to being actually more Bayesian over the years, but yeah.
I was wondering whether, do you think that actually I had an opposite thought of yours? Because I thought that, pardon my simple English and understanding of this, but that eliminating older people from your calculations and modeling is actually a plus for policymakers, because it allows to adjust public policy looking forward. Then, and we, for example, we know how many older people there are already. We know whether they will, have health issues, etc. So maybe it's actually a plus that you eliminate them in a sense, just to focus on younger people and where the social investment should go.
Yeah, exactly. If you really believe, and I think everyone really does accept this, that deprivation is this huge driver, then catching that early has been shown obviously to have a huge effect. So in that case, risk changing over time is important because you can talk about how to alleviate that risk.
It's the safest investment.
Right. In terms of policy of dividing budget across hospital areas and things like that, then you need counts. Obviously, it matters what the demographics are within that area and how that affects the number of counts that you get based on the risk. But yeah, I think in terms of interventions in other levels, I think risk is a more important measure. Yeah, it's a good point.
Thank you. Very impressive. I've never seen something like this, and I think that giving that, to make any kind of investment, so whether from private capital or public capital, at the very end, you need to know this spatial factors.
Yeah.
Because even if you look at the country level, then you have to ask, like, okay, but where should we put the cables for this wind farm or something else? And then you need spatial analysis and spatial data. So it's a wonderful example.
There's I have some colleagues, Willem Price in Sheffield, who's doing a lot of stuff about trying to estimate time courses and where interventions might have the most effect, particularly for children, and how education has an effect over life and how small deviations can change that. So they're trying to make causal inference, obviously on non-causal, non-clinical trial data, so there's difficulty in that, but it's a very interesting work, so if you're interested in that, it's a good idea to look at.
Do you think that something could be further improved using satellite image data? Well, because that's what I have seen in case of this areal interpolation techniques that you can implement around housing units, things like that.
Refine the population estimates, absolutely, yeah. No, I think Reese, who created the population estimates on that grid, which was why we were able to do the grid approach at all, it was based on sampling and census information. So a lot of work on their part, but some of it was still estimated. So I think incorporating the satellite information, as you say, density of housing and things like that, could incorporate less error in that estimation, and then that feeds through to when you're using it. I mean, some of the stuff that we've done, this was just a very basic model in that we had, where are we? Where's the actual model? So we just had an intercept, and then we had the random effect representing the effect of spatial in a particular year, and then the time effect. You're ignoring things like pollution, you're ignoring factors that are there, like you could use satellite information to look at how polluted are. There's some very good estimates that come from that. If you interpolate that with some of the small area sort of information from weather stations and things like that, that could be huge, particularly for respiratory disease, which is what we're talking about here. So that's something that Duncan is looking at a lot. And so that's, again, trying to get a continuous map of pollution potentially based on point data and incorporating some of that satellite imaging, and then using that as a risk factor in the sort of right-hand side of that model to see, okay, how much of that is just down to pollution, how much of the risk really is just coming from that, and how much is then left over that we think is stuff that we can change in ways other than reducing cars and things like that.
Just to follow that, so you provide us the reason you choose the disease, the migration disease as the main fact to study. Is it because of the aging of people around Glasgow, or is it the Glasgow? What about Edinburgh? Is it the same?
Oh, I mean,
or it just
yeah, we only looked at Glasgow for this. I mean, we had to try to do
as a first, I guess, and then to repeat the other.
The terrible thing is that the Glasgow effect is real, and we know that Glasgow would have worse risks than Edinburgh, even when you count.
You can see it at once.
Yeah.
I mean, there is not a.
But this is coming from another study that Ailey did of a very fancy way of doing spatial-temporal modeling of multivariate disease, and we were looking at, I'm trying to remember off the top of my head, we're certainly looking at heart disease, stroke, cancer, and respiratory disease. And so this was taken as something that we saw an actual more interesting one to look at because it changed a lot more over time. There was less. The risk was increasing for all the others, but the spatial pattern didn't change quite as much, which sort of makes sense if you think about it. So we did look at that before, but we haven't looked at it in this approach for over as long a time series. So it would be interesting to see, because they can say, because we saw from the multivariate approach that sometimes it's not all bad, like stroke and heart disease risk is going down for Glasgow. So yay. Respiratory disease, I'm giving you the worst case, but yeah.
It would be interesting to see some results about the study from that perspective, with that model, from the places, area, regions, when the electronic nuclear power is operating. What I heard from the physics, they said that the people living around the places are much more healthy than the others. Why? Because the natural radiation, which is very low, kills much more bacteria than on the other places and viruses.
I never heard this. Oh my gosh.
No, that's according to physics. That works
that's counter-
definitely. So what the people is really afraid of the nuclear power, they are afraid because they learn, they read, they was told that have to be afraid because of the blown, etc., which is risk is very low. But generally, for the health, is definitely positive. I'm just wonder. I'm not sure about that. But it looks,
I'd love to see a study
yeah,
about that.
looks to be
So
studied.
less respiratory disease, like some maybe a lower spike of risk for flu and things that, you know.
Maybe other
Yeah,
diseases,
yeah.
of course, was heart attack or cancer, whatever.
Yeah.
To be honest, but in general.
Yeah.
So it's
Okay, that's fascinating. I'm gonna take that away.
comprehensive.
Well, thank you for putting up with all of the equations. I know that there were a lot of them, but thank you very much for being with the audience.
I have a small thank you gift that you will remember before, so like water effect, but in like isolated camera, so you can take your hot water or tea. Yeah.
Thank you.